Hi, welcome to this lesson on Analytical Geometry, Tangents to Circles, Part 2. Let's have a look at question 5. The straight line y equals x plus 2 cuts the circle x squared plus y squared equals 20 at P and Q. Calculate the coordinates of P and Q. Okay, so first of all, the equation of that circle suggests that the center of the circle is, so let's just draw a better circle there. So the circle will have a center at the origin. Okay. So based on that circle here, it'll have a center at the origin. And then it'll have y equals x plus 2. So how do I draw that line? It has a positive gradient of 1. And it has a y-intercept at 0, 2. So that means at negative 2, 0 is going to be there. So that straight line will cut through something like this. Okay. When we say it cuts the points at P and Q. Alright. So let's go ahead and work them out. They didn't tell us which one's P and which one's Q. So for, without losing any generality, we can call that P and we can call this Q here. Okay, so there's an intersection going on between the straight line and the circle. So to find the coordinates here, I would need to equate the two equations. So now y is equal to x plus 2. So I can substitute y equals x plus 2 into the circle equation. So it's going to be x squared plus y is x plus 2 all squared equals 20. So therefore I have x squared, and then if I expand that out, I'm going to get x squared plus 4x plus 4 equals 20. So x squared plus x squared gives me 2x squared plus 4x. And then if I subtract 20 on both sides, I have minus 16 equals 0. I can then divide both sides by 2. I get x squared plus 2x minus 8 equals 0. And I need to solve this quadratic equation. Fortunately, I think this can factorize quite easily. So the factors of 8 that can give me a difference of 2 are 4 and 2. And you want a positive 2, so I would put a positive with the 4 and a negative with the 2. And if you expand that out, you're going to get x squared plus 4x minus 2x minus 8. And that'll give you x squared plus 2x minus 8. So therefore, x is equal to 2 or x is equal to negative 4. Okay, so if I put 2 here, because it makes sense, that's where the positive region is, and I'll put negative 4 here. Then if I replace that into y equals x plus 2, so if I put 2 here, it's going to be 2 plus 2 is 4. And if I put negative 4 here, negative 4 plus 2 is negative 2. Okay, and those are the coordinates of P and Q. Next, we want to determine the length of PQ. So again, P was the point 2, 4, which I'll just put over there. And then Q was the point negative 4, negative 2, which is over here. So let's work out the length of this line here. Okay, so you can use the distance formula. I'm going to use the Pythagorean theorem here in a geometrical interpretation. Negative 4 to 2, that's 6 units across. Negative 2 up to 4, that's 6 units across. So therefore, I have PQ squared, which is the hypotenuse, is 6 squared plus 6 squared, which is 36 plus 36, which is 72. So therefore, PQ is going to be the positive square root of 72 because it is a length. So I take the positive square root. That's 2 times 36. So it's going to be 6 root 2 units. Okay, that's the length of PQ. Now I want the coordinates of M, the midpoint. Okay, so there's the point again, P 2, 4. Then the point Q, negative 4, 2. So how do I find the midpoint of PQ? I use the midpoint formula. It's the sum of the x coordinates divided by 2, and then the sum of the y coordinates divided by 2. So that's going to be negative 4 plus 2 divided by 2, and then negative 2 plus 4 divided by 2. Negative 4 plus 2, that's negative 2. Negative 2 plus 4, that's positive 2. We're dividing both those by 2. So I get negative 1, 1. So negative 1, 1 is over here, and that is the midpoint. Okay, so again, the diagram was pretty rough. So if I try to draw it a bit more accurately there, so it's about there. Okay, so that's the midpoint of the chord PQ. And again, you can see it's a chord inside the circle here. If O is the center of the circle, show that PQ is perpendicular to OM. So again, we had a circle that looked like this, and we had the chord that was running through like this. Okay, so O, the origin, was the center. This was the point Q. This was the point P, which was 2, 4. And the point M we found was negative 1, 1. So we want to show that PQ is perpendicular to OM. And there's one of two ways we can prove it. So let's do the circle geometry method. So this is the geometrical interpretation. So here's the proof. So the proof is as follows. We can show that OM is the line from the center to chord PQ such that, because M is the midpoint, by definition, that means QM equals PM. So this bisects the chord. So therefore, OM must be perpendicular to PQ, and the reasoning is line from center to midpoint of chord implies it bisects the chord. Okay. Sorry, it doesn't bisect the chord. We've already said that it bisects the chord. That means it is perpendicular. So that means that the line is perpendicular. Okay, line from center to midpoint is a perpendicular line. That's the geometrical proof. What is the algebraic proof? The gradient of PQ, okay, if we work that out, so it goes up by 6 units and across 6 units. So, and because it's a positive gradient, the gradient is 1. And the gradient of line OM, again, we can do here, you can see it's a negative gradient. It goes down by 1 and moves across by 1, so it's negative 1. So therefore, if I multiply these gradients together, I get negative 1. Therefore, that means that those two lines are perpendicular as well. So there's one of two ways you can go ahead and prove that those two lines are perpendicular. Determine the equations of the tangents to the circle at P and Q. So again, here was P, 2, 4. Here was Q, negative 4, negative 2. So if we look at the tangent lines now, can you see that they're going to have a negative gradient? Okay. So again, the origin is 0, 0. That's the center. So what is the gradient of this straight line OP? Well, again, it is going 2 units across, 4 units up. So therefore, the gradient of the radius is going to be 4 over 2, which is just 2. This implies that the gradient of the tangent lines are going to be negative 1/2, because when you take the product, it gives you negative 1. And these two gradients are going to, so this is line 1 and line 2, they're both going to have the same negative gradients here, negative 1/2. Okay, and we can see that because here, the gradient of this line is also going to be 4 over 2. Well, actually, no. Let's double check that. We go ahead so fast. I'm going ahead so fast and saying it's equal. But is it actually? Let's see. Well, if I go across here, negative 4 to the origin, that's 4 units across. And if I go 2 up, that's 2 units. Caught myself very well there, didn't I? Okay, so the gradient of, I'm going to call this, let's call this line 1. This was negative 1/2. And what we have, so that's for the gradient of the radius 1. Then I'm going to call this radius 2. Okay. So don't trust your drawings just because they look rough and they look like they could be parallel, right? Trust the algebra too. That's what analytical geometry is all about. So the gradient of radius 2 we saw from here, if you rise and running, that is equal to positive 1/2. That means the gradient of line 2 is going to be negative 2. So this gradient here is negative 2. Okay, almost caught ourselves quite nicely there. Okay, so let's work with one at a time. So I'm going to look at line 1 first. That's got y equals negative 1/2 x plus c. And here I'm going to substitute the points P to 4. So I get y equals 4 x is positive 2 plus c. So I'm going to have 4 equals negative 1 plus c, so c must equal 5. And that makes sense. You can see it's a positive value up here. So therefore, that equation is y equals negative a half x plus 5. Okay, for line 2, similarly, you're going to have y equals negative 2x plus c, and you want to substitute the point of contact, which is q, negative 4, negative 2. Okay, so if you do that, you're going to get negative 2 equals negative 2 times negative 4 plus c. That implies negative 2 equals positive 8 plus c, which implies c is equal to negative 10 if you do your algebraic calculations there. So the equation is y equals negative 2x minus 10. And again, that makes sense, right? Okay, so let's just fix that up there again. So that's y equals 2x minus 10 here. So again, that makes sense. Look, the c value here is negative. So that's negative 2x minus 10, and this is y equals and then this is y equals negative a half x plus 5. Okay, so those are the two equations of the tangent lines at the point P. So at the point P, it is negative half x plus 5. And for the point Q, it is negative 2x minus 10. Okay, so the way I've drawn it is a bit deceiving because it makes it look like it's parallel, but it's not. In reality, what's actually going to happen, because these gradients are different, is that eventually, if we draw them long enough, they are going to intersect somewhere. That's what's going to happen. Determine the coordinates of S, the points where the two tangents is. So can you see that already justified exactly what I was saying here? Okay, so what's actually happening is at some point, those two tangents are going to intersect somewhere. So how do I find that point of intersection? I set the equation of the two tangent lines equal. So I set y equals negative 2x minus 10 equal to negative a half x plus 5. Okay, so what I'm going to do is I'm going to add, or multiply everything by 2 first to go to that fraction. So negative 4x minus 20 equals negative x plus 10. Then I'm going to move over negative 4x to the right-hand side. So I have negative 20 equals positive 3x plus 10. Then I'm going to move the 10 across. So I'm going to have 3x equals negative 30. And then dividing both sides by 3, I get x equals negative 10. Okay, so at x equals negative 10, which makes sense here on the x-axis, I substitute it back into one of the equations. So I'm going to substitute it back into y equals negative 2x minus 10. Okay, or you can put it into the other line, you'll get the same answer. So negative 2 times negative 10 minus 10, that's going to be positive 20 minus 10, which is 10. So therefore, the point S is given by the coordinate negative 10, positive 10. Okay, and that is the point of intersection between those two tangent lines. Now we want to show that the length of PS equals the length of QS. Okay, so S was this point up here, which was negative 10, 10. And then P was up here, which was 2, 4, if I remember correctly. Yes. And then Q was this point here, negative 4, negative 2. So again, there's two ways we can show it. The first way is the geometrical interpretation. Remember that these two lines here are essentially tangent lines to the circle, right? And what do we know about a common point outside that connects two tangent lines to a circle? They should be equal in length by the tangent theorem. So we can say that, so proof, S is a common point for tangent lines PS and QS. Therefore, PS is equal to QS by the fact, well, that's actually the reasoning for that tangent theorem. Okay, so that's all you would need. The alternative way is to work out the length of each one. So if I work out the length of PS, okay, so again, I could use a right angle triangle or the distance formula. Negative 10 to 2 is 12 units across, 10 down to 4 is 6 units across. And then same thing here. from negative 10 to negative 4 is 6 units across, and from negative 10 to from 10 to negative 2 is 12 units across. So we're going to have two right-angled triangles with length 6, 12, and this is going to be SQ, and the other one is going to look something like this, SP, and that's going to be 12 and 6. Can you see the dimensions are the same in each triangle? So when I use the Pythagorean theorem, the hypotenuse lengths are going to be the same. Therefore, we can show that PS is equal to QS. Okay, so there's two ways again, one using a circle geometry theorem and the other one using an algebraic approach. That is the power of analytical geometry. Lastly, determine the equation of the two tangents to the circle, both parallel to y plus 2x equals 4. Okay, so now we've got to think about this one. So here's the circle. Again, so it's got the equation x squared plus y squared equals 20. We want the equation of two tangents to a circle that are both parallel to this line. So if I rewrite this line, this is y equals negative 2x plus 4. So where does that straight line, that's a sloping left to right straight line because of the negative gradient. And the y-intercept is 0, 4. Okay, so 0, 4 is going to be somewhere over here. So what will the x-intercept be? So if I set y equals to 0, that's going to be negative 2x plus 4 equals 0. So 2x is equal to 4, x is equal to 2. So x2 is somewhere here. Okay, so if I draw in that line now, you can see it obviously cuts the circle, right? But now we want tangent lines that are parallel to this. So we want a line somewhere here on the circle that is parallel to this line, and another tangent line that is parallel. So from a geometrical standpoint, it looks like this one's going to have a positive y-intercept and this one's going to have a negative y-intercept. But we know because they're parallel, the gradients must be equal. So if I call this line 1 and line 2, then the gradients of line 1 will be the same as the gradients of this equation, y equals negative 2x plus 4. So the gradient's negative 2. And the same thing here, the gradient of line 2 will be negative 2 as well. Okay, and they will touch the circle at some point here. Because we know the gradient is negative 2, from the origin, so this is similar to a problem we did earlier, if I look at the radius line now from here to here, okay, because that gradient's negative 2, this gradient must be positive a half, this gradient for the radius line. And the same thing is true here. If this gradient is negative 2, then this gradient of this radius must also be positive a half. And because it passes through the center of the circle, I've got the equation for this diameter line. So remember, we're looking for equations of two tangents to a circle. We don't know these 2 points, so I'm going to call them A and B. And we know the equation of line AB is going to be of the form y equals a half x, because the gradient is a half and it goes through the center, 0, 0. Okay, so now we can do that same idea where we substitute the point y equals half x into the circle equation. So it's going to be x squared plus a half x all squared equals 20. Okay, we'll get two x values, and those will be the x values for A and B. Once we've got those coordinates, we can find the equations of the tangents. Okay, so x squared, and it's going to become a quarter x squared equals 20. Then I'm going to multiply everything by 4, so I get 4x squared plus x squared equals 80. So I'm going to get 5x squared equals 80. And then if I divide both sides by 5, 5 goes into 80 once. So then we have remainder 3. 5 goes into 30, 6 times. So you get x squared equals 16. So x is equal to plus or minus 4. So here, this one's going to be positive 4. This one's going to be negative 4. And again, if I substitute it into the line y equals half x, that's going to be 2 and negative 2. So surprise, surprise, it was these coordinates all along. Okay, it was those coordinates all along. All right, and we shouldn't have been actually quite surprised here, because if we did the working out here, we would have seen that already. Okay, but it doesn't matter. We've got those points now, so we just need the equations of those tangent lines, and we already worked them out, didn't we? There they are there, negative a half x plus 5 and negative 2x minus 10. So those are the solutions to the equations. So those are the tangent lines. Okay, just checking here. Okay, so first of all, this one here will work. But this gradient here was -1/2, so we need to account for that. So before we jump on our high horses here, let's take a step back. This one here we already worked out, -2x minus 10, because this one already had a gradient of -2 in the original question. But this one's gradient was -1/2. So if I come back to here now, so I've got a point and I got the gradient -2. So I have y equals -2x plus c, and I need to substitute the point for 2. So 4, and then I put 2 here plus c, that's -4. Let me just check there, -2x. Okay, so I'll swap those around rather. Okay, so y is 2 and x is 4, so that's -8. So if I add 8 to both sides, I get c equals 10. And that makes sense. There's 10 up there. So therefore, this equation for line 1 is -2x plus 10. Okay, so this equation here is y equals -2x plus 10, and this one here below is -2x minus 10. Okay, so just a little bit different from the first one we did, because the first one's the one gradient, remember, they were intersecting at a common point. This time, these two are definitely parallel, so they'll never intersect each other. Okay, so this is how we do these types of questions. I'll see you in the next one.